Bismillahirrahmanirrahim. This is the lecture number 1, and this would be an introductory lecture to our course. So, as our course name is Continuum Mechanics, so we will start with the Continuum Theory, and in which we will define the continuum, then continuum mechanics. So as already we know that matters are formed of molecules, which in turn consist of atoms and subatomic particles. That we have matters, any type of matter, whether it is liquid, gas, solid, whatever it is formed of molecules, and molecules consist of atoms. And then if we will divide more the atoms into, then we can say that subatomic particles, the division of atoms into subatomic particles. So it means that we will always have a distance between the particles, subatomic particles of the matter, with the help of which a matter is formed. So we can say that matter is not continuous. This is what we call the fine structure, the fine structure of the matter, that in which we are saying that we have particles and we have distance among the particles. That, but if we go for our daily life, that when we deal our daily life, however, there are many aspects of everyday experience regarding the behavior of materials which can be described and predicted with the theories that pay no attention to the molecular structure of the materials. That in our daily life, what we see, that we ignore this type of structure, this type of molecular structure, which we call fine structure of the matter. Suppose that we have water, and water is flowing through the pipe. We are considering that water is continuous, that water is behaving like a continuous matter. And also we drag we apply the force, dragging force on something in the air, that where we are also supposing that thing is continuous, that the mass is continuously distributed throughout the whole volume, that we have no distance among the particles with the help of which the particular matter is formed. So this is our daily life routine, in which we say that we are ignoring the fine structure of the matter. Although there is fine structure, that if you suppose that if you took a drop of water, then with the help of microscope you can see that there will be distance among the molecules of the water. So if we look with the help of our naked eye, then we can say that there is no distance. That if you have a drop of water, then you will say that we cannot see any distance among the molecules. This is with the help of our naked eye, not with the help of microscope. So it means that we are ignoring the microscopic structure, fine structure of the matter. So this is now we have written this theory. Which type of theory? The theory, continuum theory, the theory which aims to describe relationship between gross phenomena. Gross phenomena means that we are neglecting the fine structure of the material, that molecular structure of the material. Now this type of theory, in which we ignore the fine structure, is known as continuum theory, and the object about which we are talking is called continuum. So here what we are supposing that we have particles, and in the neighborhood of particles there are infinitely many particles. So this is called continuum theory, and the particular object is called continuum. So it can be any matter. Continuum can be any matter. Now continuum mechanics. Now continuum mechanics is simply the branch of mechanics in which we deal the mechanical behavior of the materials. Which type of materials? Which are continua. That in which, no, this is the description of the material I have written from here, in which we ignore the fine structure of the materials and suppose that mass is continuously distributed throughout the whole volume, and this material is called continuum. Now this is the, from here to here I have described materials, that I have written that that in this branch we study the mechanical behavior of the materials. Which type of materials? The materials which are called continuum, and here I have described this continuum, that what type of material will be called as continuum, that in which we are ignoring the fine structure of the material and suppose that mass is continuously distributed throughout the whole volume. So this is, we call the continuum mechanics. Now there are many physical laws in continuum mechanics. All physical laws of continuum mechanics will be expressed in terms of tensor equations. Now this is a word we are using, tensor, that you have scalar, you have vector, then you have tensor, a physical object. Scalar and vector, they both are specific examples of a more general physical object which is called tensor. So as we know that tensor transformations are linear and homogeneous. We will see this thing in our further lectures, further topics. So it means that if some tensor equation, if the tensor equation, so it means that if tensor equations hold in one coordinate system, then they will hold in any other coordinate system. So due to this invariance, we use the tensor for continuum mechanics to describe the physical laws of continuum mechanics, that the tensor equations remain invariance in all coordinate system after transformation from one to another. So it means that we will have to study first tensor. Before going on this subject, we will have to study the tensor. So to understand the tensor, we will first discuss indicial notation. Indicial notation means that we will discuss the indices, and we will see that we will have two types of indices, free indices and dummy indices, and we will discuss that which type of indices are called free indices and which type of indices are called dummy indices. So to study this subject, we will start from tensor, that we must know about the tensor. You know that what is vector and what is scalar, because in your previous classes you have already studied these two things, vectors and scalars, that you need only one thing to describe a scalar, which is the magnitude. That if you know the magnitude, it is enough to describe the scalar. But for vector you need two things, magnitude plus direction. And also you know that for scalar you have only one component, that you require only one component. And for vector you require 3 components, because you have 3 directions, so you have 3 components for a vector, to describe a vector. So if we go further, then you can say that to describe a tensor there would be 3n components. And what is n here? 3 power n. 3n means 3 power n. These are the number of components for tensor. So for scalar there is 1, for vector there is 2. Then if we say tensor, more general form, then there would be 3 power n components. Now we can have the number of components for scalar and vector from the general formula 3 power n of the tensor components. Because what is n here? N is basically the rank of the tensor. Now, as I have said earlier, that scalar and vectors, they both are tensors. If I didn't say earlier, then I am saying now that these two are the, as I said, that these two are the specific forms of the physical object, general physical object tensor. So there I mean that these two are the tensors. And which type of tensors these two are? What is scalar and what is vector, and how they are tensor? No, I have said that we have 3 power n. We have 3 power n number of components for a tensor. No, the base 3 is coming from the dimension. And what is n? N is basically the rank of the tensor. Now, how we relate our scalar and vector with the general word tensor? We will say that scalar is a tensor with rank 0 and vector is a tensor with rank 1. Sometimes we use word order instead of rank. So order of a tensor or rank of a tensor, they both have same meaning. So when we will say that scalar is a tensor of rank 0, so it means that n value of n will be 0. So if you use n is equal to 0, then we will have 3 power 0, which will be 1. So this is our confirmation that as we are saying that scalar, as we not saying but we know from our previous knowledge that scalar has only 1 component. So from here, as we have said that this is specific form of general object tensor, general physical object tensor. So number of components of scalar must be from the general formula 3 power n for components of any type of tensor, any rank tensor. So as we are saying that scalar is a tensor of rank 0, so n should be 0, so 3 power 0 is equal to 1. So number of components of scalar will be 1. Now if we go to the vector, as we are saying that vector has 3 components, and also we said that this is the specific form of the general object tensor. No, vector has 3 components. So we say that vector is a tensor with rank 1. So n will be equal to 1. So 3 power 1 equals to 3. So it means that from general formula we also have number of components for a vector is 3. So as we have seen that these two are the components, are the tensors, but scalar is the 0th rank tensor and vector is a first rank tensor. So it means that for all tensors with rank 0, they will be called scalars. For all tensors with rank 1, they will be called vectors. And all tensors with rank 2, they will be called dyadics. Their examples are stress, strain, physical quantities. And all tensors with rank 3, they will be called triadics. And there is Levi-Civita, example of the third order tensor. And all tensors have order 4, they will be called tetradics. So for example of this will be an elasticity tensor. Then as we move on for changing the value of n 1 2 3 up to so on, so there will be 1 2 3 5 6 7 order will be increasing and so on. So how we will define this order or rank, we will see this thing in our later discussion about the tensor, that how can we define the order of the tensors. For that, first we will study the transformation law. First we will study the coordinate transformation, that how we can move from one coordinate to another coordinate system. That if we have a system x, y, z and x, then another system is x dash, y dash, z dash, and we are obtaining that dash system with the help of this x, y, z after rotation with some angle, then the point in this system x, y, z has coordinates, suppose x, y, p is the point and has coordinates 1 2 3, and then what would be the coordinates of this point p in the transformed system x dash, y dash, z dash. For this we will obtain a transformation law, that how can we move, how can we transform the component, how can we transform the points from one system to another system. We will obtain for this a transformation law. Then we will use this transformation law to describe the transformation laws for scalars, vectors, second order tensor, third order tensor, and for any order tensor. So with the help of the transformation law, we will write any order tensor, and from there we will see the rank of the tensor, that how can we write the rank of the tensor with the help of transformation laws and the transformation laws. And for that we must know about the indices. Indices will tell us the rank of tensor. And when the indices will tell us the rank of the tensor, when we know the difference between dummy and free indices. So we will start from the initial notation, in which we will discuss two types of indices, dummy indices and free indices. Then we will go further. In the next lecture we will start the initial notation, in which we will discuss the free indices and dummy indices and some of their manipulation, and that how can we recognize any type of index, that whether it is dummy and free, and their summation, or how can we multiply two types of quantity with different indices, whether it is possible or not. All these things will be discussed in the next lecture. So listen to this lecture, and if you will have any question, then we will discuss it in the next lecture, tomorrow lecture, inshallah. Thank you so much.